So I will talk about topological derivators, which is the subject I am developing in PhD. But before I start, I would like to make some historical remarks considering the theory of derivators itself. So the theory of derivators was proposed and developed by Grothendieck at the beginning in order to repair some problems appearing in the theory of triangulated categories, which at the time was the central object in homological algebra. For instance, if we given an abelian category, we can associate to this abelian category category of complexes, and we can invert all the errors between complexes, which induce isomorphisms on the respective homologies. At the end of this process, we achieve a triangulated category. But it happens that, in some sense, the problems with triangulated categories is that this doesn't give to us the universal triangulated category, which is associated to our original abelian category. And then Grothendieck had a very, very simple idea, but also very deep in some sense, that instead of looking the abelian category alone, we should actually fix the abelian category, and then we should look at the categories of presheaves with values in this abelian category. So, with the domain varying for small categories. And since the categories of presheaves with values in abelian categories are again abelian categories, we can derive. We can make this process. And then we derive from that. And then we have a system of coefficients, which are connected one to another by adjunctions, precise adjunctions, which come from the functors between small categories. And this leads Grothendieck to the idea of derivators, basically. But however, so this is the basic motivating example of derivators in some sense. So the way at least as I wrote in the first slide, the way I see derivators is that if you want to consider small categories as spaces, because this is something that Grothendieck considers in his homotopological writings. If one considers small categories as spaces, then derivators are forms of cohomology for spaces. So in the sense that they are systems of Grothendieck operations from where the cohomology theories of spaces arise. For instance, it's well known by algebraic geometers that cohomology theories of schemes or algebraic varieties arise naturally, or there is a meta-structure behind them, which are the formalism called the so-called six functors, Grothendieck six functors formalism. In some sense, derivators are analogous, but considering that small categories are spaces. Actually, Grothendieck in the letter to Thomason that I'm going to mention after, he even thinks, he himself makes the analogy between small categories, seen as geometric objects and schemes. Now, in the third slide, so in some sense, the theory of topological derivators is an extension of the theory of derivators, but for toposes. But so in some sense, the theory of topological derivators could be seen as a theory of cohomology theories for toposes. But what motivates this extension? So, as I wrote in the third slide, first, the point is that Grothendieck achieves the axioms of derivators by examining the construction, this particular construction, which I told before, that assigns to each small category the derived category of abelian presheaves. This is small category. Of course, that this construction is actually defined at the level of toposes, and not only on the level of small categories. And in some sense, this construction does not depend on the small categories, but only on the toposes of presheaves over the small categories. And it happens that this is not a particular phenomenon, this derivator thereof, as I wrote in the slide, the third slide, but we can actually prove that if A and B are two Morita equivalent categories, which means that they have equivalent toposes of presheaves, okay, then they have equivalent derived categories in an abstract sense with respect to any derivator D. So this means that derivators actually depend only on the toposes of presheaves associated with the small categories and not on the small categories themselves. And it was inspired by these two observations. So what I'm trying to tell is that trying to say is that the toposes of derivators, the connection was there from the beginning, from the starting point. It's not something new in some sense. But inspired by these two observations, Grothendieck writes in a letter to Thomason. I guess that's the last mathematical communication of Grothendieck with some other mathematician. I'm not going to read the passage, but you can read in the fourth slide. It's in French, but basically Grothendieck says that we can see every derivator as a two-functor, because derivators are two-functors in some sense, as a two-functor defined over what he calls categorical toposes. So categorical toposes are just toposes of presheaf type. And that's the first remark. And the second remark is that we could expect to extend every derivative viewed that way to the whole category of toposes. So in an essentially unique way. So there is a universal way to extend a derivative to the whole category, two category toposes actually. And when I say topos, of course I mean Grothendieck topos. It was motivated, by this passage that I started to develop the theory of topological derivators, because we don't have an axiomatic, so I started to construct to propose an axiomatics. And my thesis is that when we extend a derivative to the whole two category of toposes, what we obtain is a topological derivative. And then the question is if it is always possible in an essentially unique way. So, how did I achieve the axioms of topological derivators? I rewrote each one of the axioms of derivators just in terms of the toposes, of the presheaf toposes, and the geometric morphisms, which are induced by factor between small categories. So, and I rewrote, I found equivalent assertions to each one of the axioms of derivators. We can be formulated only in terms of toposes associated to categories, small categories, and geometric morphisms. And then I obtained the axioms, so first, but before talking about the axioms, there is a notion, of course, of topological pre-derivator. It's just a two-functor from the two category of toposes with values in two category of possibly large categories. I guess that the main example we can imagine is for each geometric theory, we can associate a two-functor T mod, which assigns to each topos the category of T models internal to the topos. This is a topological pre-derivator, a representable example. And they are very important. So there is a definition in the sixth slide, I guess, but it's also a very important condition because the most difficult of the axioms of derivators, the most difficult of the axioms that I found to generalize in some sense, to extend to toposes, is this local axiom in some sense, which is the second one appearing in the definition of topological derivator. I guess that is line number 7. So, which say that for any geometric covering of topoi, the family of functors induced by the inverse images are jointly conservative. So, I'm not going to talk so much about this, but the point is that this axiom is a kind of local condition for isomorphisms between, which are, it's a way to test local isomorphisms with respect to a derivator D. So the third condition, which is very important, tells what does topological derivator do. It assigns to each topos a derived abstract, derived category, to each geometric morphism an inverse image of functor in the other direction, it's contravariant, and to each natural transformation between geometric morphisms, a natural transformation in the other direction also. And a very important axiom is that these inverse images, they have right adjoints. And these right adjoints are used to construct abstract cohomological objects in the fundamental category of the topological derivator, which is just the evaluation of the topological derivator D at the point topos, which is the category sets. So the other axioms you can see, I will not discuss all the axioms because I think you can see in the slides, and I don't have the way to, but I wrote all the axioms. So the definition, the complete definition appears at the slide 14. And I give also some examples of topological derivators, but these are very, in some sense, well known, that if C is a locally finitely presentable category, then the map, which assigns to each topos the category of sheaves over this topos with values in this locally finitely presentable category, this defines the topological derivator. There is also this the topological derivative product. So if we fix a topos, we can assign to each other topos the product. We can make the product, topological product. Okay, so we're thinking about sheaves. So, for instance, if the topos E, this topological derivative product with E is just, it just assigns to each topos X the category of sheaves over X with values in E, or the category, equivalently, the category of sheaves over E with values in X. The third example, the example C at the 15th, slide number 15, is more a construction than an example. It's a very important construction already in the theory of derivators, the ordinary theory of derivators, and happens to be also true for topological derivators, but it's much harder to prove. And at the slide number 16, I give the two main homotopical examples, which are of course these derivatives there are, which takes the derived category to be the sheaves. And this is really important, the most important actually example, which is the derivator, the Ibu-Zizhou derivator. So to each topos X, we can associate the category of simplicity of sheaves over the topos or simplicity of objects, and then can make the homotop theory of spaces internally this topos, an internal way of homotop theory. And this construct, and then we have a class of equivalences between simplicity objects, which are the Ibu-Zizhou equivalences. We can invert this Ibu-Zizhou equivalence, and at the end we obtain a derived category, which is the hot of X, the homotop category. Homotop types internally to X, topos X. And this, of course, defines the topological derivator. And, well, there are other things about this topological derivator is very special. For instance, as I begin to write in the slide number 17, I show how can we define total homological objects to each topos with respect to a fixed topological derivator. And we can define a notion of the equivalence, which is a kind of Artin-Mazeroux equivalence, homological equivalence, with respect to the topological derivator D. And we can also define a related notion of the equivalences to each topos. I think that we fix a base topos and we can define a related notion. And at the end, in the last slide, I mentioned a very important theorem, which allows us to compare the internal equivalence with equivalences in the simplicial the topos of simplicial objects in a given topos X with the equivalences over the topos. So it's a kind of using this process of the total topos associated to fiber topos. So, and the theorem, it says just that if we have an arrow of simplicial objects which is an equivalence equivalence, then and we associate this the geometric morphism of total toposes over X, then this turns to be a de-equivalence, a cohomological de-equivalence with respect to every left topological derivator via Z0. So this is very important. It in some sense it indicates some kind of universality of this topological derivator hot. So and it opens the path in some sense to give an answer for the Grothendieck questions in the letter to Thomason. So I guess that. Thank you very much.